Hello everyone. For this video today we are going to be taking a look at the sine and cosine ratios. Now in the previous videos we've taken a look at the tangent ratio, and just a quick review, remember the tangent of an angle is the ratio of the leg that's opposite that angle divided by the length of the leg that's adjacent to that angle. So the tangent of an angle is the opposite leg length divided by the adjacent leg length. And today we're going to be looking at sine and cosine ratios. So first of all, I have a diagram here, and the question I want you to think about is, why won't the tangent ratio help if you want to find the values of x and y in this diagram? And let's just assume that since I didn't give you a measure, let's look at angle n, and let's say that angle n is a 28-degree angle. So why would we not be able to find the values of x and y in this? Well, we know that the tangent ratio for angle n would be the length of the opposite leg, which is PM, right? If here's our angle, then this over here is going to be our opposite leg. So PM's length divided by the adjacent leg, which of course is going to be segment NM. But we know the angle N is a 28-degree angle, and we know that would be equal to PM over NM, but that would be Y over X, and we would have two unknowns, right? So there would be two unknowns in this equation that we would need to set up. We learned in the last video that if we want to use like the tangent ratio to find a side length in a right triangle, we need to know the angle measure and one of these two numbers. So that way we would only have one unknown in this little equation here. So the tangent ratio wouldn't help us in this situation. But lucky for us, there are two other trig ratios that compare the lengths of the legs of a right triangle, if you want to add in that word right, the lengths of the legs of a right triangle to the length of the hypotenuse of the triangle. So these are called the sine and the cosine ratios, the sine and the cosine ratios. And that's what we're going to be spending our time taking a look at today. Now remember that in this triangle that I have down here, the opposite angle from, the opposite leg from angle A would be segment BC. Segment BC would be the opposite leg, or we usually just write OPP. And segment AC, right here, that would be the adjacent leg. And of course, since here's our right angle, across from that right angle is segment AB, and that is going to be known as our hypotenuse. So let's go ahead and define the sine and cosine ratios. The sine of angle A would be equal to the length of the opposite leg divided by the length of the hypotenuse. Or in this picture, the sine of angle A would be equal to the length of BC divided by the length of AB. The cosine ratio of angle A is going to be the length of the adjacent leg divided by the length of the hypotenuse. Or in this case, the sine of angle A would be the length of AC divided by the length of AB, the adjacent leg divided by the hypotenuse. So now if we combine that with what we learned in a previous video about the tangent ratio, we now have the basic definition for all three primary trigonometric ratios. As you go on in your math classes, you'll learn that there are more than three trigonometric ratios, but the three that we just learned about, sine, cosine, and then tangent, are usually considered the primary trigonometric ratios. And oftentimes you're going to hear those ratios get shortened to a little phrase called SOHCAHTOA. SOHCAHTOA. And you'll hear that a lot going forward in your math classes, this idea of SOHCAHTOA. And here's what it stands for. It's a nice easy way of remembering the definition for sine, cosine, and tangent. Because the SO part tells you that the sine ratio is found by doing the opposite over, so I'll put over in parentheses, the opposite over the hypotenuse. The ka part is the cosine is the adjacent over the hypotenuse, so we can see C-A-H for ka, and the TOA tells you that the tangent ratio is the opposite over the adjacent. So SOHCAHTOA, you'll want to commit that to memory. That's going to be something that's going to be helpful for you in a lot of different scenarios, not only in this class, but in Algebra 2, and for some of you in classes like pre-calculus, and even if you get up to calculus, you'll want to know what SOHCAHTOA stands for. So SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Now, we already learned a few things that were helpful to know about the tangent ratio, and those properties and characteristics for the tangent ratio apply for the sine and cosine ratios as well. This means that for every angle that has a certain measure, I say that has a measure of x degrees, where x could be any number, every angle that's, let's say, 28 degrees, or every angle that's 63 degrees, or whatever x could be, all of those angles have the same value for their sine ratio, and they would all have the same value for their cosine ratio. So, like for instance, if you typed in your calculator the sine of a 50-degree angle, as an example, the sine of a 50-degree angle will be equal to about, I should do the squiggly equals, about 0.7660. And so every 50-degree angle, if you divided the opposite side by the hypotenuse in a triangle that has a 50-degree angle in it, you would always get about 0.7660. And the cosine for that 50-degree angle would be about, again, so this means that if you were looking at a right triangle with a 50-degree angle and you divided the adjacent side by the hypotenuse, you would always get an answer that's about 0.6428. And I just got these values by using my scientific calculator. I just typed in sine of 50 and cosine of 50 to get these values. So that's the first property that we need to know about sine and cosine, that every angle with the same measure will have the same sine ratios and cosine ratios. And secondly, we can use what we call the inverse sine and cosine ratios to find the measure of an acute angle if the appropriate side lengths are known. So for instance, if we know that the sine of angle A is equal to x, then that means that the inverse sine, which looks like this usually written out, and if you're looking on your calculator, this is the function that you're looking for in your calculator. The sine inverse of that value x tells you the measure of angle A. And similarly, if the cosine of angle A equals y, then if I take the cosine inverse of what y is, it tells me the measure of angle A. So these inverse these inverse functions also apply for sine and cosine just like they did for tangent. So let's look at a quick example using this idea of SOHCAHTOA and inverse sine and cosine and so forth. We have to find the values of the variables in this diagram, and you can see we have an n that we need to find and we have a p. We know the length of the hypotenuse of this right triangle. It's 100, so I'm going to write down, just to remind myself, that's my hypotenuse. And we have the measure of angle P here as 50 degrees. So let's quickly label the other two sides from the perspective of angle P, the 50-degree angle. We know that this side over here, segment MN, or where our P is, that is going to be the opposite leg because it's across from the 50-degree angle. And N, or the length of segment MP, is going to be our adjacent leg because it's the leg that's next to the angle. And of course, this side, like we've already labeled, is our hypotenuse. So we know that there are three trig ratios that would apply here. Let's look at what those would be. We would know that the sine of angle P would be opposite, or segment MN, over hypotenuse, which is PN. We would know that the cosine of angle P would be adjacent, or segment PM, over hypotenuse, which is segment PN. And we would know that the tangent of angle P would be the opposite, or segment MN, over the adjacent, which is segment PM. Now if we start filling in some values or variables for these three measurements that are involved in each one of these ratios, the angle measure and then the side lengths, we should be able to tell what we can use to find p and what we can use to find n. Let's start over here with tangent. If I fill in 50 for the angle measure, and I put in, for mn, I put a p, because in my picture that's what the length of mn is, and for pm I put n, I'll notice that I have two unknowns in this one. So this is probably not what I'm going to try and use for finding the length of p and n, because there is an infinite number of combinations that would work there. And I don't know exactly which one I'm looking at in this picture. If I move backwards one to cosine, and if I say the cosine of my 50-degree angle is equal to Pm, which is n, over Pn, which is 100, now I notice that I have an equation here with only one unknown. I should be able to solve this. And I'm actually going to use this idea of proportions. I'm going to put this thing over 1, and I'm going to cross multiply. So n times 1 gives me just n equals cosine 50 times 100. The way I'm going to write that is I'm going to write 100 times cosine 50. And that's what I'm going to type in my calculator. Some people are going to be tempted to right away try and turn cosine of 50 into some long decimal, and then they have to keep track of that decimal through the whole problem. I would really recommend you just leaving it as cosine 50. It's easier to remember, it's easier to write, you're less likely to make a mistake by writing down a wrong number from one step to the next step. So I just leave it as cosine 50, and I get to this step where my n is isolated, and I grab my calculator and I say, well, actually I already know what it is up here, right? I already know my cosine of 50 is up here because I had used 50 degrees as my example. But I'm just going to grab my calculator. I'm going to type in 100 cosine 50, and it tells me that n is about, and I'm using about since I'm going to round this off to the nearest tenth, it's about 64.3. So I know my n value is about 64.3. Let's come over here and let's use sine. This should tell us our value for p. I'm going to say the sine of my 50-degree angle is equal to mn, which is p, over pn, which is 100. And again, if I put this over 1 and cross multiply, that isolates the p, because p times 1 is just going to give me p, and I will have 100 sine 50 over here. So now I can grab my calculator and I can type in 100 sine 50, and it's going to tell me that it's about 76.6. So now I use sine and cosine to find my values of p and n, and it worked because I knew the angle measure and I knew one of the lengths involved in my sine ratio and my cosine ratio. I knew the hypotenuse of this triangle, and so hypotenuse is involved in both sine and cosine, so I kind of knew that that would probably be the one that I would want to use. I would want to use the ratio that involves the side length that I know when I start my problem. Let's look at example 2 on your notes, and let's find the measure of each acute angle in this diagram. So in this diagram I have a right triangle and I know two of the sides, but I don't know anything about the angles. I can actually use the idea of SOHCAHTOA. I'm going to go ahead and write that out. I can use this idea of SOHCAHTOA to find the measure of angle P and the measure of angle N. So here's what I'm going to set up. I'm going to say that from the perspective of angle P, right, this would be the opposite leg, and of course this is the hypotenuse because it's across from the right angle. So I can say that the sine of angle P would be whatever mn divided by pn gives me. So in this case, if I fill in the parts that I know in this, it'll tell me that the sine of angle P is equal to 18 over 60. And like we just talked about a few minutes ago, if I know what this sine ratio is equal to, if I know what the sine ratio of P is equal to, I can use the sine inverse function, and I can use this ratio right here. I can put 18 over 60, and again, you could go ahead and type in your calculator 18 divided by 60 and use that decimal right here. But I think this is probably a strategy that will lead to fewer mistakes because you're less likely to accidentally write down a wrong number if you just keep it as 18 over 60. Sine inverse of 18 over 60 is going to be what the measure of angle P is equal to. So now what I do is I grab my calculator and I do sine inverse of 18 over 60, And for most of your calculators, when you do sine inverse, which is for most of you, it's the second key, and then you hit the sine key, because right above the sine key, you'll say sine inverse like that. When you hit second sine, it usually opens up a parentheses. Your calculator will show something like this on your screen. Sine inverse, open parentheses. Then we're going to type 18 divided by 60, and we're going to close that parentheses. We got to make sure you close that parentheses because you want to tell your calculator to do the sine inverse of this whole thing, not just the 18 part. So when I do the sine inverse of 18 over 60, it gives me a measure of about 17.5 degrees for the measure of angle P, about 17.5. Now I could set up another trig ratio, so I'm going to write this in over here. I know that this is now 17.5 degrees. I could set up another trig ratio to find angle N, or I could realize that that's actually not necessary. I can just go ahead and I could use the fact that these three angles need to add up to 180, or that since it's a right triangle, these two angles have to add up to 90, and I could say that the measure of angle N is going to be equal to 90 minus the measure of angle P, so that means that the measure of angle N is equal to 90 minus 17.5. And 90 minus 17.5 is going to give me about, or well, I guess I can say it's going to give me something that's equal to 72.5 degrees. So the measure of angle N is 72.5 and the measure of angle P is 17.5. And again, I found that using the sine ratio for angle P, since when I started the problem, I knew the opposite side and the hypotenuse. I could have set this problem up originally, so I'm not going to work through the entire problem, but just to show you that if I wanted to, I could have originally set up the cosine of angle N as mn over pn, right? Because from angle N's perspective, this is the adjacent side. So if I was doing the cosine of angle N, that would have left me with 18 over 60 for the value of the cosine of n. So I could have done cosine inverse of 18 over 60, and it should have given me the same answer that I got right down here. So these problems, you do have a little bit of a choice about how you're going to start the problem, whether you're going to use a sine ratio or a cosine ratio, or maybe sometimes a tangent ratio. It just depends on what angle you're trying to find and what parts of the triangle you know from the perspective of that angle that you're trying to find. Okay? Now there is one more example on this note sheet. I'm going to save that for in class, so I'll work through this example with you in class. But hopefully the idea of the sine and cosine ratio now makes a little bit of sense. Again, you're going to want to make sure you commit that idea of so, ka, toa to memory. You're going to want to memorize that because it's a nice, easy way of remembering the definitions for sine, cosine, and tangent. Okay, folks, I will see you next time.